In this video, we're going to be looking at how you can find the angle between two lines that are expressed using vector equations. So here I've drawn a line 1 and a line 2, and I've labeled the angle between them. When we talk about the angle between two lines, it's always going to be the angle that's measured between the parts of the line that indicate the direction that they're going. So each of these lines is going to have a direction vector associated with it. L1 has a direction vector here of B1 that says it's going this way, and L2 has a direction vector of B2, and that's what says it's going that way. And so the angle that we're finding will always be the angle that falls between those two direction vectors. So here it says that they're going sort of upward. L1 is going up and to the right, L2 is going up and to the left, and so it'll be the angle measured between those two parts of the line. Now, of course, we've already seen something that connects angles to vectors in the form of the dot product. So we know that the dot product of two vectors u and v is equal to the product of their magnitudes times the cosine of the angle in between them. Now, each of these lines is expressed with a vector equation. The line L1 would be expressed with the vector equation r1 is equal to a1 plus t times b1. And the line L2 would be expressed with the vector equation r2 is equal to a2 plus s times b2. So each of these lines has a position vector, a, that's going to get us onto the line in the first place, and then a direction vector, b, that tells us how to move along the line to find the other points. As far as which one of those vectors is relevant to the dot product in question, well, we already kind of addressed that by saying it's the angle based on their direction vectors, so it's the direction vectors we're going to have to use with our dot product to find our angle. So I'm going to rearrange the dot product and reference that I'm using those direction vectors, which yields this equation for finding the angle between two lines. So if we're keeping this equation on hand to find the angle between two lines, let's say that I provide equations of two lines. So the first line has the equation given here, r1 is equal to 3, 2, negative 1 plus s times negative 504. And line number 2 has the equation given here, r2 is equal to 1, 3, 4 plus t times the vector 3, 1, 0. So again, we're going to focus exclusively on our direction vectors, which means we're looking at negative 504 and 3, 1, 0. So I'll take the information from those direction vectors. You can see here I have vector b1, and this is vector b2. On the top, I'm finding the dot product of those two vectors, and in the bottom of this fraction, I am determining their magnitudes. So I have the magnitudes of both vectors now. The magnitude of the first vector is root 41, and the magnitude of the second vector is root 10. And so by evaluating, I know that cosine of theta has to equal negative 15 over root 41 times root 10. So if I find the cos inverse of both sides, what I end up with is an angle measurement of approximately 137.8 degrees, which, for the purposes of expressing that in three significant figures, I would probably just go ahead and round that to 138 degrees. So that's the angle between those two lines. Of course, there are two special cases to keep in mind when you're looking to find the angle between two lines. First of all, if the direction vectors have a dot product of 0, it means those vectors are perpendicular, which means the lines themselves are perpendicular. And so you know then the angle between the two lines is going to be 90 degrees. If you notice that one of the direction vectors is a scalar multiple of the other, that tells you the direction vectors are parallel. What that means is the lines themselves are parallel as well. And so here you would say that the angle between them was 0 degrees.